Hi everybody, this is David Paul. Thanks a lot for joining us today. And Chris Gallagher, I'll be introducing him in just a moment. So we're here to talk about fractional electrodeionization. It's going to be a 40-minute presentation. I'm going to give you a 10-minute intro, and then Chris is going to give you the details on the fractional electrodeionization, or FEDI. And then we'll have at least 15 minutes, maybe 20 minutes of questions and answers. So just type your questions into the question box, and then when we get to the Q&A section, then Chris will be answering your questions. So this presentation is recorded, so it'll be available sometime tomorrow, Friday at the latest. Here's the website. You'll be sent a thank you email tomorrow from me, and it'll have a PDF of this presentation, so you won't have to keep any notes. You'll get the PDF of this presentation. And just so that you're aware, Qua Group, which they're the owners of and the patents holders of this FEDI technology, David H. Paul Inc. and the Qua Group do not have a financial relationship. So we're just presenting this seminar or this webinar so that our clients and Qua Group's clients have this information. So here's just a few things on me. I've been in water treatment a long time, long before EDI was around. Chris, I've known Chris for many years. He's a great guy, and he has a lot of experience as well, and he's published a lot on EDI, and he's installed some of the biggest and first and EDI units around the country, around the world. So he'll be coming in and talking in just a few minutes. I'm going to give just a real brief overview. This particular slide, don't worry about it. This is so that you have some words when you get the PDF and you look at it tomorrow or whenever you look at it. So I'm going to start with just electrodialysis, because electrodialysis is the predecessor, and it just makes EDI a lot simpler to understand, I think, when start off with electrodialysis. So EDI is going to be the next advancement over electrodialysis, and then Chris will be talking about fractional EDI, which is another step. Okay, so with ED, as we'll see with EDI as well, you have a cathode and an anode. This is direct current. So the cathode is always the cathode, the anode is always the anode. And then in between the two electrodes, we put cation transport and anion transport membrane sheets. So for those of you that are familiar with ion exchange, a cation transport sheet would be made essentially out of strong acid cation resins that are in like a plastic matrix. And then the anion transport resin membranes would be made out of strong base anion resin embedded in a matrix. Water does not pass through these membranes, only the ions. So cation transport means that cations, which are positively charged ions, can pass through the membrane. Anions cannot. An anion transport membrane allows anions to go across it, but will not allow cations. So again, in between two electrodes, we have alternating sheets of cation and anion transport membranes. There are spacers in between these sheets that lets the water get in between, but we're not going to, just to keep the picture simple, I'm not going to put those spacers in. So the feed water is going to enter between either the membrane sheets or the membrane sheet and electrode, and is going to pass from one end to the other. So in the feed water we have cations, here calcium, magnesium, and sodium. We have anions, sulfate, chloride, bicarbonate, and bisilicate or silica. So the cations are going to be attracted to the cathode, and we see that since we have a cation transport membrane sheet there, the cations can pass across the transport sheet, the cation transport sheet, but then once it gets into this section, it cannot pass through an anion transport sheet, so now it's trapped. Same thing happens with the anions. The anions are attracted to the anode. They can pass through anion transport sheets, but they cannot pass through cation transport sheet, so they're trapped in there. So the channels where the ions leave, this is called the dilute stream. So this would be the feed stream on the left, and here we have the dilute stream, or the purified water, on the right. Where the ions are trapped, these are going to be called waste streams or concentrate streams. So this is how we're removing ions from water. Well, the ED, electrodialysis, this is a low purity technology, and really it's the kinetics. You have ions that have to travel some distance through water, and that's going to take some time. So for drinking water or a lower purity water, that would work. But now EDI comes along, and it's a brilliant technology. But this is a high purity water technology now, and we'll see why. So we're still going to have exactly the same situation. We're going to have two electrodes, a cathode and anode, and in between we're going to alternate cation and anion transport membrane sheets. But now, to make it high purity water technology, we're going to put strong acid cation and strong base anion resin beads, just like for those of you that have mixed beds. This would be the same type of resin that you'd have in a mixed bed. They aren't actually in this configuration. This is just to show that you have strong acid cation beads and you have strong base anion. Each manufacturer has their own way of putting these resins in between the membrane sheets. But now this is a high purity water technology, because now when an ion comes in, so if it's a calcium, and the calcium comes into the strong acid cation, it now is going to transport very quickly, almost like electricity, boom, boom, boom. It's going to go from the functional group to the next functional group, the next functional group, to across the membrane, and it's gone. So things happen very, very quickly, and you're able to get high purity water out of EDI where you could not get high purity water out of ED. So feed water, now we're talking RO permeate. Feed water is going to enter the mixed bed or the mixed resin portion. So what's going to come out is, high purity water. Your ions are going to get trapped in the waste streams in between the membrane sheets, and we can call those concentrate streams, or we can call them waste streams. And then we have some special things, we won't go into it today, some special things that occur in the electrode bleed channel. So so that's a special situation we won't go into. So basically it's RO permeate is going to go into all these channels, but we're going to end up with the high purity channel, the waste channel, and the electrode bleed channel. So if we look at this from left to right, we'll see that in an EDI stack that your easily removed, charged ions are going to come out very, very quickly. And then in the next layer, you're going to get more difficult ions to come out of the feed water. And that's what we're showing here. So actually somewhat similar to what you would see in strong acid cation, strong base anion resin beds. But the real difference here, and the reason that we don't have to regenerate EDI units, is because once we start getting into this difficult area, then the electrical potential actually splits water molecules, H2O, into hydrogen and hydroxide, which is exactly what we regenerate strong acid cation beads with, which would be acid or hydrogen, and the strong base anion beads, hydroxide or caustic. So the water splitting only occurs at the locations where you have the strong acid cation and strong base anion beads or membranes touching each other. And it's only in the dilute areas. You're not going to have this occurring in the front end. So in the dilute chamber, what our goal is to have a small working bed. And what that means is this is where, you know, all of your calciums and sulfates are easily removed. Most of your ions are easily removed out here. You want the biggest polishing bed that you can have. That gives you the highest purity water. If you let your RO unit head south and it's making worse water, then we'll see that's probably going to make us have EDI effluent that is not as high a purity. So if there's higher feed TDS, so the RO unit is not putting out as good a water, then we have a smaller polishing bed and the water isn't as good. Okay, so that's my quick rundown of how EDI works. And now we're going to turn this over to Chris, and he will give you the rest of the information on fractional EDI, and then he'll do Q&A, and then I'll come back and finish it off. Thank you so much, and here's Chris.
Very good, David. Thank you very much. Very good, everyone. Thank you for attending, and I hope everyone can see my screen. So today we're going to talk about I'll say a revolutionary advancement on the EDI technology. And we refer to that as FEDI. And just a little bit about QAR itself. QAR is a advanced membrane product supplier. We have 4 different products. We have a QSEP, which is a hollow fiber UF. We have the FEDI technology, which we'll talk about today. We also have a ceramic membrane, and then we have an MBR product, the MBQ. So these are all, I'll say, advanced membrane technologies, but today we'll focus on the FEDI. So FEDI. So with the FEDI technology is the next generation of EDI, I can say. We have a patented dual voltage process where we can control the voltage on the 2 different stages or regimes inside the EDI stack. That allows us to control removal of ions, and we can take a higher hardness tolerance in feed water than other EDI suppliers. Gives us a quick startup. It also helps us reduce or give us a node cleaning. And we have a couple of case studies we'll look at. So as I mentioned, there's 2 different patents governing this EDI technology. One is for the process itself, and one is for preparing the ion exchange media. And then the stack is also CE certified, which is really important these days since it's a global technology, and when you're working in the power industry or pharmaceutical industry, getting certification is very important. So we do have a CE certified the EDI stack. So let's take a look at this. And David talked a little bit about electrodialysis and how that evolved into EDI. So EDI did, I'll say, come from ED technology. And inside EDI, actually there is some ED principles taking process. It's a combination of chambers that are filled with ion exchange media or conductive filler. And we refer to it as a deionized water compartment. And you'll hear a lot of different names for the diluting compartment, deionized water compartment, purifying compartment, and they're all analogous to each other. And the same on the reject compartment or the concentrating compartment, or as David referred to it as the waste stream. So the combination of ion exchange, resin media, and ion exchange membranes. And QAR's EDI stack does use ion selective membranes and a form of conductive filler or ion exchange media. Now, the device itself needs a potential or a voltage. And all EDIs are governed by current efficiency. And we won't get into too much of the details of current efficiency today, but it pretty much comes down to a higher current efficiency means that the current generated from the voltage, and you need the current to do the work, a higher current efficiency refers to ions being actually transported. So when you work at a higher current efficiency, you're removing ions, or ions are transported through your media, through your respective membranes, and into your reject compartment. When we look at running at low current efficiencies, that's when water is being used actually to split water, or I refer to as polarization of water, into its constituents of hydrogen and hydroxyl ions, and you have these regimes of an acid and a caustic. So the electric current is used to unidirectionally move ions across the membranes, and it actually regenerates the resin. Right? If you're splitting water into an acid or a caustic, that's exactly the chemicals you would use to regenerate ion exchange resin. So this is a typical EDI stack. Most EDI suppliers out there today, they'll run EDI stacks with an upflow parallel configuration, where it's you're running from the bottom upwards. And that's one reason you do that, is to remove any gases formed and to remove any bubbles or air in the system. We've referred to the concentrate chambers. Typically, it'd be a one pass or one flush through. Same thing for the dilute. And what we do is we refer to EDI stacks with cell pairs. And the cell pair comprises of a diluting compartment and a concentrating compartment. You have multiple cell pairs that is typically in a plate and frame device that are all held together. Now on each end, as David alluded to, we have an anode and a cathode. Most EDI suppliers control or have an anode or have an electrode flow, which is the water that flows through your nodes, anode and cathode, and then leaves the stack. And then the second stream would be the concentrate compartment, and then you have a product. So some EDI suppliers today actually combine the concentrate and the electrode, so they have only two different streams entering and leaving the EDI device. And there's pros and cons to that, and we'll get around to them. So what differentiates the FEDI, the fractional EDI, to the traditional or some of the older EDIs out there is it's an advanced two-stage process. What I mean by an advanced two-stage process is this two-stage process happens in all EDI devices, where you have a working zone that removes strongly ionized species, and then you have a polishing zone, as David referred to it, and that actually removes some of the weakly ionized constituents, such as silica, CO2, and boron. However, the fractional, the FEDI process, we can actually control, we apply a voltage to each of these different zones or regimes. So we can control the current to run at a slightly higher current efficiency in one zone, so we do not split water, and then we can control the polishing zone, where we can run at a lower current efficiency, where we want to split water, so the resin becomes regenerated, and you can ionize weakly ionized constituents. And the other beauty of this FEDI process is, in the reason why we can get a higher hardness, is we're running at these higher current efficiencies in this working zone, and we can actually take this reject off midway through the EDI stack and introduce a second concentrate flow or stream into the working zone. So this removes any scaling potential right away in your first zone or in your first part of the stack. and it allows the polishing zone to split water, and the likelihood of scaling is minimal or none because you're removing all your ions midway through your stack. So we control these two different zones by removing the ions in the first one, polishing in the second one, and letting that polishing zone do what it does best. Split water or polarize water into hydroxyl ions and hydrogen ions, and ionize all the weakly ionized constituents. And it can provide some of the purest water in the world. So as I mentioned, the hardness, we refer to it as a hardness removal zone, or I'll call it the working zone. We typically will use a lower electrical driving force. And what that means is I refer to as a higher current efficiency. So all these divalents and sodium chloride and some of the monovalents are removed. And also the reject pH is acidic. It eliminates the scaling potential. Again, giving the FEDI that higher tolerance for these divalents that come in. And it prepares the weakly ionized impurities for stage 2 removal. So a silica removal zone runs at a higher electrical driving force, and this creates the water splitting. We actually regenerate the resin in this polishing zone. And when you regenerate the resin, it does a couple of things. One, the resin itself actually expands, right? When the resin goes from an exhausted state in a salt form to a hydrogen or hydroxyl state, it actually expands. And what it does is actually give very good packing density inside that compartment. So it gives you it lowers the electrical resistance. And when I refer to current efficiency again, it's almost looking at Ohm's law. You have E equals IR, and you want the stack to have low electrical resistance. So by the water splitting, you're getting a very compact, low electrical resistance zone. You can run at a higher current, get additional water splitting, and additional removal of these impurities, that the silica, the boron, and the CO2. And as David mentioned, in electrodialysis, electrodialysis came out in the 50s, I believe, and ionics was one of the first people to introduce it. It's one of the first technologies to purify water outside of filters. It was well before the reverse osmosis or pressure membrane systems out there. So ED's been around for a long time, and it's always been a rough demineralizer. Very robust system, used the same principles, but it would never be used in a high purity water application because you'd never want it to split water, because that's what with the scaling would occur. You'd have these higher pH regimes mixing with some of your divalents with maybe some alkalinity, and that's what forms scale. So the beauty of the FEDI is having these two distinct voltages and pH operating zones. The working zone taking the primary load, the regeneration zone, the polishing. One of the other things it does too in that polishing zone is we can remove some ionic TOC. Now TOC, which is total oxidizable or total organic carbon, it's kind of a catch-all, right? There's all different size molecular weights in their form, and there's all different forms of TOC. But because the FEDI itself can control that zone, and we're polarizing more in that stage 2 zone, we can remove a lot of TOC. So depending upon what that TOC is, we do get good rejection of organics. So here's a side-by-side comparison. So the traditional EDI on the left and the FEDI on the right. Now today, just to go back a little, some of the older legacy EDIs out there required salt injection and maybe even a recycle of your reject or concentrate. And that came from looking at velocities in the EDI, and also having some of the EDIs had a very high electrical resistance in their reject compartment, which required them to inject salt and actually do a reject recycle. But over the years, it's been developed and been known that the flow velocity isn't like similar to a membrane process like an RO. Anyone skilled in the designing RO systems know that you need a certain velocity in your reject or concentrate compartment so you don't perform scale on the surface of the membrane. EDI is not I'll say a pressure membrane system. It is not a filter. So it's been found over the years that having a higher velocity in the concentrate is not necessary, but having the right size or a membrane distance of membranes in your reject compartment can certainly lower your electrical resistance. The closer the membranes, typically lower electrical resistance. So the FEDI stack is an optimal design of the reject. So we do not need a reject recycle. We do not need salt injection. And again, most devices out there today don't need it. Some people actually use a ion exchange filler or a conductive media in the reject compartment. Because of the design of the reject compartment of the FEDI, we do not need that additional media. We still have very low electrical resistance. So again, I look at it as having less components makes the EDI easier to use. In this case, less is more. So on the left we have, I'll say, a traditional electrodeionization cell. On the right, the FEDI. And we're showing here that as the water flows through this, they control only one zone. They use one voltage, splitting water in their polishing zone. They're removing the ions in their working zone. But they're taking some of the divalents and they're bringing them right down to where the polishing zone is. And that's where your scaling takes place. When you split water in the EDI, you have these I'll say isolated pH areas. In the bulk solution, there might not be a bulk solution of a high pH and a low pH. You have certain regimes of it. And that's where the scale takes place. It's when the calcium and the magnesium come in contact with hydroxyl ions, higher alkalinity. If you're splitting CO2, you're turning it, typically what happens is CO2 goes in a carbonate form, becomes ionized. When you start combining hydroxyl ions, the carbonate, and then you're taking your calcium and your magnesium, you bring it down into that zone, that's where you start having scaling problems. So as I mentioned earlier, the beauty of the FEDI is we control both zones. And right now we'll just talk about the stack as a single flow, but we can do some pretty cool things with this as well. We control the flow in it, but I'll get to that in a few minutes. So in this case here, we control the hardness, and we can remove the constituents, any of the foulants. And even if we're removing some of the foulants that could contaminate this zone, we're removing them before they come in contact with the resin and before these foulants come in contact with the second reject zone. So what we're doing is we're allowing this zone here to do what it does best: split water, remove weakly ionized constituents. And this has been done in the lab probably years ago, and I hate to date myself, but I was fortunate to be on the team that commercialized EDI. We did a lot of work in the lab. And years ago, it was very difficult to manufacture EDI. But because of the advancements of polymer and extrusions and molding processes, most EDIs today are very robust. And so because of the advancements in the manufacturing process, FEDI was the first one to come out with this particular and commercialize this type of technology. And it's definitely an advancement on your options today. So let's look at some of the applications for FEDI, very similar to what we see today by other EDI suppliers out there. We have the power industry. And the power industry is very concerned about silica. Anyone that's worked in that industry or designed systems for the power industry, they typically look at silica. And they're very concerned about silica because they have very tight silica specs. They take water, they turn water into steam, and they use the steam to power turbines, and then they condense it down. And they have a closed loop system, right? They recirculate their condensate back, they turn it into steam, and they have this closed loop type of system. One of the things they can't afford to do is have silica precipitate out in the turbines because it reduces the life of the turbines and the components of the power industry. So the power industry is concerned about silica. We'll look at the pharmaceutical industry, and I'll have to say EDI was first accepted in the pharmaceutical industry. And I'll have to say that it also, Millipore was probably the first to commercially introduce it. And when it goes into the pharmaceutical industry, the beauty about the EDI or FEDI technology in the pharmaceutical industry is it's not so much of the water product, the product quality it can make, because we're only looking for, say, a 1 microsiemen, though the water that it produces is well over the 5 and approaches that 18 megohm holy grail type of water. But the beauty about a EDI or FEDI technology in the pharmaceutical industry is you bring this system into the pharmaceutical site or biopharma site, and you validate it once. So validation and documentation is extremely important in the pharmaceutical industry. One of the things they don't like doing is bringing equipment in and out all the time. It requires shut down the pharmaceutical plant, which they can't afford. They have to revalidate or follow ion exchange resin. So they were the first to probably welcome EDI because it was a technology where they didn't have to swap out ion exchange bottles. It produced and exceeded the pharmaceutical requirement specs for TOC, microsiemens. So they liked it because it was a product where you could bring it in, you validated it once, and it made continuously high purity water that exceeded their specs, and you only needed to validate it once. In the semiconductor industry, again, when they begin to do manufacturing, both in the micro, when we talk about microelectronics, it's actually going to be nanoelectronics now. They're getting very tight with this new nanotechnology out there, but it produces water that's greater than 60 megohm, and depending upon the design of the pretreatment, you're approaching that holy grail of 18 megohm. So the semiconductor industry doesn't want to anything they can measure, they don't want in the water. They actually set standards for the roadmap for instrumentation companies, for where in my early days, ppms were great. They went to ppbs, parts per billion, evolved into parts per trillion. And today the semiconductor industry is looking for parts per quadrillion. And they give these guidelines to the instrument companies to develop instruments to measure it. They know it's coming, and so they kind of set this roadmap for a futuristic measurement for instruments in the industry. The food and beverage uses high purity water. They use it for rinsing of tanks. They use it for putting pure water, excuse me, and diluting food products and beverage products. So the use of high purity water is well known, and EDI or FEDI applications, the FEDI technology fit all these applications. It definitely can replace mixed bed polishing after RO. And we talk about, let's talk a little bit about pre-treatment, because we talk about after or post-RO systems. I'll have to say when EDI was first introduced, EDI actually competed with some of the reverse osmosis systems out there, where the pre-treatment was multimedia and scavengers, carbon tanks, and softeners. And EDI actually worked very well on just media filtration. However, what you found out on some of the early systems, and again, I hate dating myself, but this is back in the early 90s and the late 80s, that all these media type filtrations, they weren't absolute technologies. You would get breakthrough of hardness and organics, and EDI would follow. So all EDI applications today that I know typically require RO, either single pass or double pass, as pre-treatment. But I think we will see a few things in the near future where with robust technologies like FEDI, there could be other applications out there that don't need RO, but that's a presentation for a different day. So if the FEDI technology we can replace, and today most EDIs are interchangeable. You look at the three major players out there, they all offer replacements for each other, and FEDI does as well. So the FEDI technology is something that should be considered when your EDI system needs to be replaced or upgraded. And then also condensate polishing. That's an application that EDI we have looked at. However, if you look at condensate polishing and some of the solvents and the chemicals used in that business, it's an application that needs to be well engineered. So FEDI or QUAR, we do have a EDI projection software to help with your design of your EDI, and I think that's on our website, and you can download it, and it would certainly help with designing and putting in your constituents from your RO, and gives you a nice projection on the amount of stacks and sizing of power supplies. So as a lot of us know, the advantage of EDI, I won't get too much into it. Again, FEDI as well as the other EDI devices out there today, it replaces mixed bed. It's a chemical-free type, very environmentally friendly device. You don't need acid and caustic. It replaces the mixed beds. You don't need neutralization of the waste stream. You don't need any type of transportation of chemicals or waste off the site. Most EDI, I know when it first came out, the price of EDI, I'll say over the past 20 years, has dropped considerably, where most of the payoff for an EDI, comparing it to a mixed bed, is well within one annual period. So if you're comparing or you're considering a mixed bed technology or a service DI type, certainly if you're looking over a 1 year or 12-month period, EDI is extremely cost competitive these days. It's a continuous process. It's very simple. It's been very simplified, I'll say, over the past few years. It gives you very consistent quality. I have a couple of graphs to show you some changes in feed water compared to the EDI product or FEDI product. It reduces installation costs, and some of this, anyone skilled in the art of EDI knows the benefits of it. And so I'll move on to my next slide. So some technical specs for the FEDI stack. Again, it looks very similar maybe to some other products out there. It's a, we've kind of gone over this, the two zones on it. We have one conch in, one conch out. So it's a plate and frame device. Most of plate and frame, some might have a circular design. It's still considered a plate and frame, I'll say, where we have I'll say a closing mechanism with two plates, almost looks like a heat exchanger, plate and frame heat exchanger. We have an anode, we have a cathode. As I mentioned earlier, the beauty of the dual voltage is we control both. The FEDI can also be used as a single voltage, where you can run one voltage and run it through as a standard or I'll say some of the existing EDIs out there today. We have multiple cell pairs in this plate and frame device, and one of the things that makes FEDI very robust is we don't need, some of the EDIs out there today use some type of O-rings to prevent leakage. The early EDI designs may need that because the big concerns of the EDI, and if anyone has been around as long as I know, that some of the first EDIs out there were very prone to leaking or weeping, as the manufacturers would call it, electrical shorting. The EDI, the FEDI design actually use a very unique process in manufacturing where our stack is almost snapped together, where we snap our diluting compartments and concentrating compartments, which is a little bit thinner than the diluting compartments. And we have multiple cell pairs like others out there. Depending upon the FEDI product you choose, there's different flow rates, and we normalize for a particular flow rate per cell pair. And there's so many cell pairs between this plate and frame device. So some of the FEDI models you'll see a FEDI 2 dual voltage for high hardness, does not require any type of salt injection. We can take up to 3 ppm of hardness, and I have some specs we'll show. We have the FEDI 2 single voltage. This simply for lower hardness applications. Perhaps your RO, you're running on a softened feed, or you're using some type of higher reject or higher reject membranes. So your calcium or your hardness in your RO design is low enough. We can run it as a single voltage. And then we have a unique thing where we can use the stack, and we call it a high flow operation, after a double pass RO. Many EDI supplies today require double pass RO to get the product water from the EDI. So a lot of people will look at different products out there. Some people may claim to run at higher hardness levels. However, they run at lower recovery modes, and we'll show the recovery in a minute. I got to the specs on it. And then we have a RX for pharmaceutical application, where we have heat sanitizable EDI, very popular in the pharmaceutical industry. The FDA likes to use heat to sanitize and kill bacteria. So heat sanitization, very popular in the pharmaceutical world. We don't need any O-rings. Our system is extremely robust. We have a special spacer design to prevent leakage. And that means that we don't need the O-rings. Again, less is more in manufacturing. We have central ribs which separate our two stages. These ribs provide additional strength. Some of the existing or legacy EDI, I'll say, out there, a lot of the problems in the past were maybe you'd get water hammer or overpressure, and you'd damage the EDI spaces. And you wouldn't just damage the EDI spaces, you'd move the resin around, which is something you don't want to do. So our the additional strength in ours comes from central ribs that separate our two compartments. And all our compartments are molded. And again, because of the advancements of molding and polymers today, it's very easy to make a very consistent, reproducible, robust FEDI stack. So some of our, just the connections you'll see out there, ports, we have 1-inch NPFTs. We like to use standard threads. You don't need any type of special connections or adapters to go from our stack to a typical piping. We have a 1/2 inch on the concentrate or reject compartment. And then we have an electrode rinse, as I mentioned. And I think the electrode rinse is very important because, as I said, that's where some of the scale can start forming before it forms internally in the EDI components or EDI's, the diluting and the concentrating compartments. It can follow in your electrode rinse. And if you're not measuring your electrode rinse, you don't know that it's following. And I've autopsied numerous stacks, and I know some of the suppliers out there have switched to an electrode rinse because what happened was the electrode would plug up, and if you weren't measuring it, you'd have a reduced flow in your electrode, which caused heat generation, gas formation, and a catastrophic failure of the EDI stack. So I always think that an electrode rinse and measuring and monitoring it is extremely important in the EDI process. So this is a single voltage mode. We have the RO permeate comes in, run through the dilute. We have an electrode rinse, and then it goes through one concentrate to the second concentrate, and then leaves as a one stream. Well, actually, there's two streams in this case. I apologize. So in the single voltage mode, we're running at running the concentrate both stage 1 and stage 2. So we have the reject from both. So you can run in a single voltage mode by still controlling your concentrate in both compartments. And then we have the product. And then a lot of times it's recommended to do a rinse in case the EDI is shut down. You want to make sure you have when you're within the specifications of the application. And so a lot of times there might be a rinse just to get the product up to at the quality that's required. So this is a single voltage high flow mode. And this is pretty cool. This is actually, and as you saw, we have the two stages where we control the concentrate. You can also control the dilute or the deionization stream. You run one stream in, we split it off, and you actually, and I'll call it residence time. You decrease the residence time of your diluting, or the time the water's in the diluting compartment, by half. But you can get twice the flow from a FEDI stack by controlling both. So we have these two stages where we control the concentrate in both. We control the diluting or the deionization, and we actually control the voltage. All three help to make FEDI what it is today. So here's a dual voltage mode where we have the electrode, we have one diluting compartment, and we control the voltage on each stage. So some of the typical operating parameters that we look at, everyone looks at feed conductivity equivalents these days, which includes CO2. CO2 is one of those constituents in water that you certainly need to do a grab sample and measure. It depends upon alkalinity and pH of your system. We can take up to 1 ppm. Silica, total hardness is calcium carbonate, take up to 3 ppm. Organics, 500 ppm. No one likes to see really any heavy metals in their system, so we keep that number very low. And then chlorine. Chlorine is one of those things where all EDIs out there are affected by chlorine, and I'll add chloramines. Chloramines are used today in municipalities, and it's really caused an upset in a lot of designs out there because chloramines can be removed in EDI, and the chlorine can oxidize the anion resin and irreversibly damage the EDI stack. So we definitely think chlorine and chloramine, probably one of the biggest problems you'll see in any type of EDI failure today is people not measuring or controlling their chloramine level or chlorine level. And even the RO membrane can become damaged. And the unfortunate thing is I always look at EDI as an instrument. It detects what's going on upstream of it. So all your pre-treatments almost can be detected. If you have a problem with your RO or softener or chlorine, EDI picks that up very readily. Feed water SDI, you always like to keep it very low. As I mentioned, EDI is not a filter. It does not remove particulates. Even an RO does not like to remove particulates. So you like to, the SDI should certainly be less than 1 unit. So our product on it, we can get up to 18, a properly designed system. You can certainly get up to the 18 megohm level. Silica levels less than 5. Parameters for voltage, we typically look at anywhere on a typical system, might be a 300 to 450 volts DC. We can go up to 500 volts DC as well if needed on either stage. And our currents, you're running within anywhere from 1 to say 4 amps. We like to run the current low in that stage 1 if we're on a dual voltage, and then run it lightly higher on the second so we get that water splitting. Our stacks range anywhere from a low of 5 gallons a minute. We do a maximum product of 22, and our high flow modules even go higher. And then there's always minimum flow rates, right? You certainly need, one of the things you never want to do is run an EDI stack, extremely low flow rate with a very high current on it. You can create gases in it, you create heat. You like to keep the flow rate always running through, especially in the electrode rinse. And we run recoveries up to 95%. That 95% is actually a high hardness. So a lot of people out there kind of fool around with saying, oh, I can take a 2 ppm calcium carbonate, but you're running at maybe an 80% water recovery. So we can run a very high water recoveries with taking that high hardness. Our pressure drops can range from 15 up to 60. Our pressure drop across the stack is closer to 40 or 50. So you always have a differential pressure between your inlet and outlet. And we can go up to 100 psi. Here's a nice picture of a FEDI installation. You can see very simple, nice and clean. And that's what you like to see. Again, anyone skilled in the art of EDI and knew there's some out there that could get quite convoluted with the piping and voltage and the power supplies and the piping. We like to, again, keep it very simple. When people ask about, what's the payback on EDI or a FEDI to primary mixed beds, it always, as the flow rate gets higher, EDI or FEDI technology certainly becomes more cost competitive. So when you're running at a 5 or 10 gallon a minute type flow rate, payoff on that would be a little bit longer, but as you get to higher flow rates, your payoff definitely is it leans toward a FEDI type design. CIP protocols, similar to others out there. Most of our stacks we don't require cleaning just because of our design. If needed, acid cleaning for any type of mineral deposits. And I find sodium chloride is actually very effective. So sodium chloride is probably one of the more effective, and it's very, it's not a hazardous chemical. And then we always require flushing afterwards. Quick case study here, the Brazos electric plant. This is probably the longest running FEDI reference. It's over 6 years, 2 trains of 165 GPM each, running less than 10 ppb silica. We're running about 0.07 microsiemens, which is about 14 megohm. Quick graph on silica. You can see our silica. You can see a little silica fluctuation. This is over about a year period. Our silica changes, a little fluctuation in the silica. And you can see our silica out. The feed silica has changed, and our product silica has actually stayed about the same. It's always been under 10 megohm. We look at conductivity. Our conductivities have been stayed the same, even though you see a fluctuation in the RO permeate, and that could be due to startup and shutdown, and things of that nature, changes in feed water. And you have these fluctuations, and you see a very consistent line here of a roughly 14 type megohm product. A couple other select references. This is a single pass, very big. It's one of the largest EDI installations in the world. We have nine skids of 465 gallons a minute. South Coast Steam Power, Puerto Rico, 400 gallon, 400 gallon a minute. Allowed the plant to be very environmentally friendly, right? No chemicals. And another refinery out in Egypt. And this handles variable inlet conditions. And that's one of the things. You can have variable inlets on your RO permeate, your feed water changes, and the EDI is a great buffer to smooth that out. Quick cut sheet. This is a FEDI 2 spec sheet. It's on our website, and certainly can download it and give you the details. It's a little difficult to read in the presentation. And then we have the high flow, as I discussed. Very smart design here. We're running on a 2-pass RO. You can double your flow. Very economical, very smart design. So with that being said, I appreciate everyone's attendance. And if you have any questions, I think you guys will send them over to me, I believe, through David and his counterparts. Thank you very much.
Thank you, Chris. We only have 5 minutes for questions. But if there are more questions, the way we'll do this is we'll go ahead and end it right top of the hour, and then Chris will continue answering questions after that. So if you have to go at the top of the hour, then feel free. You can always come back to the recording if you want to get some other question and answers. So type your questions into the question box that you have, and then Chris will read the question and then he'll give you the answer. Again, we've got about 4 minutes now, and then we'll end it, and then we'll come back to the Q&A.
Okay, my question, question number 1, can FEDI be used for softening only? Yes, we can design a FEDI, again, using RO though. We always still recommend an RO as pre-treatment. If you do want to run a FEDI just to remove post-RO dyed valence, we certainly can design the FEDI to do that. And we can actually use a high flow module where we can run and use both zones where each zone is just used to remove dyed valence. Another question, does FEDI have any applications in the desalinization industry and wastewater treatment industry? Right now, FEDI is being used for high purity water applications. Again, using RO as pre-treatment. So right now, for the desalinization, it is not being used. As anyone knows about desalinization, pre-treatment is always, again, I'm very heavy on pre-treatment type of engineer. So desalinization is very difficult. You definitely need some great pre-treatment on that. But no, we have not used it. Another question, has FEDI been used for deionization, for deionizing UF-treated fruit juice waste for recovery of sugar? EDI has been tried, but high calcium levels cause problems. No, right now we have not. I would certainly be interested in this further. I have used EDI in my past on non-water applications where we desalted or dehatched components. So certainly get in touch with me and we can see what we can do for you. But right now we have not. Can FEDI voltages be controlled to enable selective ion removal? Yes, and that's the beauty of these two stages and having these two electrodes of the dual voltage, where we can control the ion removal in either stage, primarily probably the first stage, because when you begin to split water, it's a lot more difficult. But yes, we can control that ion removal in the first stage.
Chris, let me break in here, and let's end this for everyone, and then you can come back to any other questions, so those of you that want to stick around. Just for your information, David H. Paul Inc., we give EDI hands-on training and classroom training. So if you want to go to our website, you can see what we have available for next year. And if you would like more information on FEDI, you can contact Chris. You can go to the Quad group. So we want to thank you so much for attending. Chris, if you'll continue with your Q&A.
Very good, David. Thank you. Okay, I have another question. Please talk about the cost differential between EDI and FEDI, capital and operating cost. So if we look at the two, it's definitely dependent upon the application. If you're looking at a double pass RO design where we're using the high flow FEDI stack, we're extremely cost competitive to the traditional EDI and typically a lot better. Again, it depends upon flow rates and the application. You know, starting with your water analysis, what you need to remove from the water and what you're trying to achieve is definitely dependent upon the design. So we'd have to design a a power supply to accommodate whatever the application may be. But when it comes to a single or a single voltage design, again, FEDI is very cost competitive. We understand the nature of the business, and because of some of the way the EDI stack's designed and the manufacturing of it, we're very cost competitive today. Another question? Do we have any farmer applications installations in North America in a typical lifespan? Yeah, I'd have to get back to you on the installation. We definitely have a heat sanitizable EDI that's been run through multiple cycles, and it's on the data sheet. I apologize, I don't have it in front of me. We do have a few farmer applications. A lot of them are international, and I'd have to do some research and grab some from the U.S. Can EDI remove ammonia and CO2 in process condensate streams? Yes, it can, and that's something I've looked at for quite some time. Ammonia can be ionized and removed in EDI, FEDI applications, as well as CO2. It's definitely dependent upon the concentration of CO2 and ammonia. And the problem with the condensate applications is what I've seen in condensate, and again I talked about the closed loop application, is because there's so many different chemicals used, and you pick up contaminants in condensate polishing, it can follow the EDI. So a lot of times you'll see, you'll always see, even on ion exchange processes, a good amount of filtration to remove any particulates before your condensate polishing, ion exchange. But yes, it can remove and work well in some condensate polishing applications. Does the technology require more electrically than conventional EDI? Very good question. On our dual voltage, we do require a second power source. For one of the Brazos plant, I believe, we use a dual voltage. It still became very, very cost competitive. It produced and exceeded the water requirement the client needed. But yes, in some applications where we need to run the dual voltage, we'd run a second power source. Does the resin need to be replaced periodically? If so, what would be the typical frequency? So in most EDI applications, and they don't, and I know early on we always looked at swapping out cell pairs and resin in the field. Today, you'd swap out the EDI module, not just the ion exchange resin. Because of our design, we have very low fouling tendency because we control the voltages, and because of the flow rate and the design of the spacer. Our systems are running out there 5-6 years or longer. And again, it always depends, and I mentioned about EDI being used as an instrument that detects problems in your pre-treatment. But if your pre-treatment is working, and even if we do get, and we showed in some of those slides, variations in TDS or silica, the EDI is typically working, and the pre-treatment's designed well. There's EDIs out there I know of that's worked for quite some time, longer than 6 years. Another question we have here, how do we know that the resins are recharged or not? Very good question. There's actually a calculation we can do. It's probably not necessary, but as I mentioned, the resins in, say, stage 1, some of those resins are in the exhausted state, but some of those are still in the regenerated state. As you get to stage 2, you can look at current efficiency. where you look at the water entering the device, the water leaving. So it's the work done, right? The work to remove the ions is what you take for what's coming out, which is virtually zero, and the amount of ions you have entering the stack. And you look at flow rates, you look at Faraday's constant. It's a complicated, I can certainly share the equation with you, but it would certainly tell you the amount of current efficiency you're using. And the current efficiency is telling you how much water splitting is occurring in the stack. Another question, how does it save energy compared to EDI? Well, if you look at the energy an EDI uses, and you look at the kilowatts and the amperages, it's very minimal. We use the same amount of amperage. What we do is actually control it. So if you look at the energy, we just have more control of where the energy is produced. So if you look at an EDI today that may run 3 to 5 amps for a certain flow rate, we'll actually control that. Where our 3 to 5 amps is only used in 50% of the stack. And half the stack is actually only using a lower amperage. So if you add up all the kilowatts, we're probably controlling or using less kilowatts than the average EDI out there, because we can control those 2 stages. If we're running at a single stage, we're probably running about the same. Again, current efficiency governs all EDI devices, and it governs electrodialysis. All right, very good, everyone. Thank you for your questions. Very good questions today. Feel free to get in touch with me, and you have my contact information. And very good. I appreciate everyone's attendance.
Okay, thank you, Chris. And thanks, everybody, again. If you haven't done the polling questions before, please do it now before you leave. And thanks so much. Bye-bye.